thanks for inviting me to come out and talk. I'm really excited to be here. And so my topic tonight is going to be from a startup perspective, from the place where we've built a system from scratch that serves up NLP models in a strictly cloud-based environment. So by way of introduction, I'm a senior data science engineer for a startup just a few blocks from here called Casbon. And what we do is, if you'll imagine, just for the sake, just humor me for a minute, if you'll imagine that there's a really large machine somewhere, and if you could just throw anything at it, press a button, and boop, 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 out pops an answer to any question that you want. That's sort of along the lines of what we're trying to do. We're trying to build a lot of those machines to answer very specific questions, and we do that in a language-independent way. So the format of my talk tonight, I'll try and keep it under 30 minutes to get you guys out of here. I don't want to bore you to death. But I'll give you a little bit of background about the problems that we're trying to solve and the technology that we've chosen to help us solve those problems, why we chose Spark specifically, and some of the machine learning components that we're using and integrating into our system, and then the challenges of using Spark specifically for NLP use cases. So I'll talk about some of the projects we've worked on. We've looked at using Twitter data. We've looked at trying to correlate the intention, trying to understand when people are intending to buy cars and separate that from when they're just saying positive things about cars or trying to sell cars. And you can imagine that might be very useful for anyone in the consumer product business to be able to predict the type of growth that they'll see, the type of demand that they'll see for their product. We've also been able to analyze global health trends and look at epidemic tracking, and that helps aid workers respond in a more efficient way. We've also looked at improving IVR systems. Everyone's familiar with that frustrating phone call where you're just not getting where you want to go. Our system can help improve those and give you a less frustrating experience. We've also looked at analyzing company performances based on news that comes out across the globe in many different languages. If you're managing a portfolio of stocks, it can be very helpful if you understand the perception of those companies across the globe. We've looked at identifying risks to the supply chain based on news stories that come out in certain domains. We've also looked at how users respond to code pushes in video games. So based on the types of things that people are saying on Reddit, how are those video game changes being received? And one of my personal favorites is the work that we've done with UNICEF. We've worked with a few of the divisions in Africa to help them prioritize the incoming messages coming from their community. And what we do is we provide this rough classification, that way they can understand which of the messages that I need to respond to right now and which of them can wait. We help them automatically classify things, that way they can best use the resources that they have available to them. So how do we do it? How do we tackle these use cases? The NLP is a little bit different than other types of machine learning because it's generated directly from humans. And human data can be very, very messy. Because humans are involved in the creation of the data, in the interpretation of the data, humans are a very critical piece of the puzzle, and so they're also very central in how we build our models. We're big proponents of using crowdsourcing in order to create our training data sets. And we use, this process is known as adaptive learning, and it's where, in order to build your models, you start out with a pool of data, and you want to, as quickly as possible, build up your training set. So you decide what questions you want to put in front of humans. You send that out to the crowd. You generate a small set. You build models out of that, initial models, and you use that to decide what the next set of data is that you want to put in front of humans. When you go through this process, you follow this circle over and over again, and each time you go through the process, your models get a little bit better, and the set of data that you're putting in front of humans is a bit more intelligent. And after a while, you have models that are a lot more accurate, and by involving humans in this process and involving the crowd, you can do this a lot more quickly. So in a bit more detail, whenever we build a machine learning product, there's generally three large components. There's the data set itself, there's the models that you build, and there's the prediction that comes out at the end. Now a lot of people, when they build out a project, they start with a data set. They may have something that they think is useful, but they're not sure how or why. But we found that it's better if you start from the prediction side. So the very first thing you want to do is you want to define your goal based on what you want to get out at the end, what that final number is going to be. And once you've defined that, it should be pretty obvious what data set is most conducive to that. Once you know what data set you want, you can start ingesting it and cleansing it and getting it to a point where you can work with it. And then you can start generating your training data set. And this is where you decide the types of labels that you want, the types of classifications that are most useful for building your statistical models, and the types of questions that you want to put in front of your humans that will build you the best models. While you're creating that training data, you always want to make sure that it's high quality, because let's face it, this is the crowd. Sometimes you can see some strange things, so you always want to be monitoring that, because that's your gold standard. That's your set that you're creating your data from, you're creating your models from. And the next step is to actually create the mic cut out. Can y'all still hear me? Maybe if I talk a little louder, is that better? Or is this better? Does this thing work?
I don't know if that's switched on.
Hello. Oh, it says dead battery. But the next step, once you've gathered some training data, is you want to actually generate your models. Once you've generated them, you can try different parameters. You want to analyze how they're performing, and this is the step that we call hyperparameter optimization, and this just involves trying out lots of different parameter values in order to get the best prediction results. After you've created some initial models, you can then, this concept of intelligent queuing is deciding what to send to your humans next in order to build up this training data set, because you don't want your models to have all the same type of data. You want it to be very representative of the domain that you're looking at. So you gather more of your training data set, build more models, and sometimes at the end, if your statistics don't exactly represent the domain, you can add a few rules to sort of bump up your accuracy a little bit more. And then the last step is, the whole point is to give it unseen data. So to send data to your models and get predictions and get that answer that you're looking for. Now those steps don't always happen in order. We usually iterate through many of them, especially between creating the training data and ensuring that it's of high quality, creating models and going through the process of optimization, changing parameters, and getting better accuracies out of it. And in general, all of these steps right here, we'll iterate through those over and over again. So what type of platform can support that type of process? That's sort of a rough overview of what we're trying to accomplish. And these are some of the tools that we use to accomplish that. So from a user's perspective, a user request will come in as an HTTP request. We're a startup, so we're not in the business of running data centers. Everything we run is on the cloud. So it'll come in through Amazon's Elastic Load Balancer. That'll get sprayed out to any number of EC2 instances that we may have running at any given time. And it'll go to our workhorse, which is our REST API. This is where our main code base is, and this is what performs most of the work. So even when users come in through our user interface, it sends out API calls behind the scenes. And the main data store that powers that is a simple relational database, pretty standard, MySQL, with any files that don't necessarily belong in a relational database going into S3. So with that combination of tools, why did we choose to add Spark to things? Well, we really like Spark because there's a wide variety of algorithms in MLM, and it's one of the most active projects in the ASM, I believe the most active project, which means that they're always improving those algorithms and adding more. So we really like that choice. We love that it's open source because we can see inside. We really like the implementations that we've seen, and we can push out our own patches, we can make suggestions. The community is very open to improvements, and we really like that we can fix things ourselves or add new algorithms. It's also sort of been accepted as the industry standard for a lot of the algorithms that they've implemented. And some of the NLP specific toolkits were put out there by universities. They were developed and they're managed as research platforms. And that's all well and good, but we really like that even though Spark started out at UC Berkeley, it's now turned into a platform that's meant for enterprise use. And Databricks, IBM, many different companies actively ensure that it remains an enterprise platform. Another consideration, scalability is one of the most important things that we deal with. And the fact that it's baked into this platform, it's one less thing we have to worry about. We really love that. So how are we using it? We're using it for our core machine learning functionality, and that essentially breaks down into these three components. There's a feature extraction phase where we take a text-based piece of data and we turn it into something that a model can understand, and that's a vector of numbers. There's the training portion where we apply a label to that, a classification, and we build statistical models out of that. And then there's the prediction phase, and that's what we send back to our users. That's where we get to answer the question that they're trying to ask. So specifically, some of the functions that we like within Spark ML are TF-IDF for feature extraction. We also are very interested in word-to-vec and using deep learning. Dimensionality reduction, we have our own functions for that, and we're really interested in how that compares to Spark's implementation. And there may be some cases where one works a bit better than the other, and we want to have more than one option. For training, logistic regression models are sort of our go-to. We really like those. We also like SVM, naive Bayes is pretty standard, and LDA for topic modeling. Prediction is pretty straightforward. Works just like it says on the tin. Evaluation metrics help us with cross-validation, and during the hyperparameter optimization phase where we're building models, evaluating their performance, tweaking parameters, deciding which direction to go in with those parameters, and then rebuilding models based on those metrics. So here's an example of a really basic, sort of typical feature extraction pipeline that we might use. But you start out with a single tweet. Let's say you pull this down from Meetup, it comes in JSON format. The first thing you want to do is extract the portion of that tweet that you're interested in. And that may be certain pieces of metadata like the country or the language or just the content itself. The first thing you would do is extract the content, and then you would break that into pieces. That's called tokenization. And those are more standard pieces that make a bit more sense. So maybe the stem of your words or certain components that are more typical across different types of text. And then you break those down into, you might be interested in unograms or bigrams, trigrams, all of the above. You may concatenate both of those together into one very large feature vector. But once you get to this stage in the pipeline, you're ready to do your feature lookup. And that essentially boils down to just assigning some sort of arbitrary index. And what that allows you to do is move from it being in a textual context into a numerical one, so that it's ready for training. So the feature extraction pipeline is all about just creating your feature vector with characteristics that are representative for the domain that you're training with. So the training step, the first thing you do is you take that feature vector and you add a classification. And this is just the number that you use is completely arbitrary, but it has some sort of meaning based on the goal that you've defined and the type of prediction that you're doing. So Spark calls it a label point, and it's essentially just a label along with a feature vector. And you send an RDD full of a bunch of training data, full of those into this logistic regression algorithm. And it will spit out a model. And that model is something that you can use for prediction. So what we do at the end of the training phase is we take that model and we store it. We save it for a rainy day, ready for prediction, ready to be pulled into the cache and called up by our users. During the prediction phase, this is where we have a different piece of text. It should still be in the domain that you use for your training, but it's something that you've never seen before. You don't want to use any type of data that you use for training your models. And you run through the exact same featureization pipeline to generate a feature vector that looks very similar to the ones that you use to train your data. The dimensions should be the same thing, and it should be very much in line with your training set. So at the same time, once you have your feature vector, you want to reach back into your model storage, grab that model that you've trained, and send in that feature vector. You'll receive a prediction back, and that'll be some sort of classification. And you do a lookup to understand what that number means in the context of the problem that you're trying to solve, and that's what you send back to your user as their result. So in order to provide this type of prediction, the training phase is something that may take days or weeks or months. The training phase is something that you can do in batch. We will take a bunch of training data, we'll put it in front of humans, we'll spend quite a bit of time generating that model and tweaking it and getting it to a point where the accuracy is high enough. But the prediction phase is something that happens ad infinitum into the future. So once we have our models, we may update them and refresh them over time, but they'll basically stay somewhat stable. And the prediction phase is what we don't batch. The prediction phase is the portion where we need to respond in real time. So how do we provide online predictions with Spark? Spark was really designed for working with large batches of data and not necessarily returning thousands of predictions a second. So something that we've found in serving up these online, these really quick responses to predictions is that data frames can be very slow if you have small data. So we really love data frames, and they're really awesome if you have a lot of data. But if you're talking about a single tweet and you really want to serve up that prediction within a few microseconds, data frames aren't necessarily the best approach. So we did some very unscientific and informal tests on one of our engineers' laptops, and we found that a typical prediction using just a vector took, on the order of 300 microseconds, which is completely reasonable and within our limits. And that same prediction using a data frame took an order of magnitude longer. It's definitely not something that we would find suitable for serving up thousands a second. So in general, for predictions, we don't use data frames, and we'll go directly into the underlying NLP implementation and just try and get around using RDBs and the overhead of instantiating the Spark context and all the overhead that goes along with data frames. Otherwise, we do really love them, and they're great for training. So this kind of brings up the question: how do we fit Spark into our existing system? Our entire application is not written on Spark. I would find that pretty difficult. If anyone has done it, I'd like to hear how you did it. Before we added Spark, we had a core API, a code base with all of this existing functionality, including a lot of algorithms that we've written ourselves and dimensionality reduction pieces that we're not sure if Spark is going to replace yet. And so what we concluded was that we were really in need of this persistence layer, and that acts as sort of an insular layer in between our main code base and all the different components that we might want to use for the machine learning components. So the core algorithms, we wanted to be able to integrate those as easily as possible. So that allows us to gives us access to everything within Spark, and it means that we can use all of the components that we've already built and any other new package that we decide we want to add to our toolkit. That gives us the flexibility to not have to change too much within our core functionality and just swap out machine learning components. So why do we even really need a persistence layer, and how does that enable us to use Spark? Well, we have thousands and thousands of models. We serve many different clients, and for each question that they want to ask, we may iterate through the creation of models, hundreds of times, and we want to version all of those. We want to be able to go back in time. We have lots and lots of models, and that isn't necessarily what Spark was originally designed to do. And adding this persistence layer really helps us to operationalize that and make it easy on our ops engineers, make it easy for us to deploy, and it just means less pain for our engineering team. It also means that we can embed it within different platforms. So right now we're using Docker containers, but we're also interested in running some of this on Lambda, or perhaps offline or on device if we go on-prem to any of our clients. And related to that, we're interested in having a sort of standardized save and load framework. So we're using input-output streams rather than having to rely on the existence of a file system. I think Spark is pretty heavily dependent on being able to write files. somewhere. And so we like some of the independence that that gives us. We also want to provide our data scientists with new features as quickly as possible. And we don't expect them to learn a new framework every time something comes out. We want to make it as easy on them as possible. And so this gives us a means of quickly integrating new features and making it simple for them to add it into their projects and iterate through the model building process. And the other component is a standardized and abstracted logging framework. I think Spark really likes Log4j. We prefer Self4j because then you still have access to Log4j. You have a few more options and you can be a bit more flexible with it. But this persistence layer just helps us to keep everything nice and neatly packaged, and it allows us to scale out as needed no matter how big our client base grows. So just to conclude, analyzing human language is not the simplest. So NLP is a bit different just because you have this sort of complex, jumbled mix of ideas, this sort of stream of thought consciousness that you have to sort of package into a square chunk that you can then fit into a mathematical model. And it's really exciting that we're using some of the coolest pieces of Spark in order to help us do that, because it's really improved our system and helped us build out a much faster and better system than we ever did before. So that's about all I had. I'll open the floor now to questions if anyone wants me to go into a bit more detail.